this rotation matrix in one shot by choosing the right alpha, beta, and gamma over here, and then doing the reverse rotations. So that's one problem of this sort. But also a problem of this sort is the inverse kinematics of a robot arm. So if this is x and y, and if this is theta 1 and theta 2, L1 and L2, I have that the end position here is L1 cosine theta 1 plus L2 cosine of theta 1 plus theta 2, and y is equal to L1 sine theta 1 plus L2 sine of theta 1 plus theta 2. So this is a nonlinear function. This would be called f of theta, right? Being f1 of theta 1 and theta 2 and f2 of theta 1 and theta 2. It's a nonlinear function. We have sines and cosines in there. And in this context as well, we may want to, we have a known position that we want the robot arm to reach. We have an x comma y that we want the robot arm to reach, and we want to find out what the angles of the arm need to be in order to place the hand there, right? So both this problem and the original problem that's in the paper that motivated all of this discussion are both of this form. So what do we do? How do we solve for a value of q that will satisfy that equation? Well, one way is Jacobian iterations. And it's easier to draw with this than it is with this. But basically, you can imagine picking two initial guesses for theta 1 and theta 2, evaluating it in this equation, and seeing where the hand ends up when you substitute those angles in. But this is where you want to go. So what we can do is we can actually define a path from where we are, where the end of the hand is now, to the point that we actually want to go. Okay? So this path, we can call that x of t. It starts out when t is equal to 0 over here, and let's say when t is equal to 1, it ends up where we want it to be. Okay? So we can define a desired path from where we are to where we want to be. So that means that what we can then do, and so here t is really not real time, it's an artificial time parameter that we're introducing, ranging from 0 to 1. And within the context of that artificial time, we have this equation, which we can linearize. In other words, we can, what's called rate linearization. Which is just the chain rule. So we're going to take the time derivative of both sides, and we get x dot over here is equal to, now the chain rule, we have a function of time. And so what we get here is a matrix, and the entries in that matrix look like partial f, partial qi. So each column in this matrix, I'll write it out as columns. This is partial f, partial q1 is the first column, partial f, partial q2 is the second column, and we work all the way to partial f, partial, if there are n coordinates, we will have, if there are n thetas, we will have n columns in this matrix. So in this problem there are 2, so n is equal to 2 in this problem. In this problem over here though, we have alpha, beta, gamma. We have 3 parameters, so n is equal to 3 over there. So we have x dot is equal to this times q1 dot, q2 dot, down through qn dot. Okay? So the shorthand for this matrix right here is called the Jacobian matrix. The Jacobian matrix depends on Q. This Q1 dot, Q2 dot down to Qn dot, that is just Q dot. And the idea of Jacobian iterations is that you start with this equation. So I'm just going to suppress this dependence on Q. I'm just going to write this as x dot equals j times Q dot. Okay? Now remember, we have defined x of t. So we know what x of t is. Therefore, we know what x dot of t is, because we've defined x of t. So x dot of t is always pointing from where we are to where we want to be. It's a velocity vector pointing from where we are to where we want to be. And so these Jacobian iterations work by updating Q at the next instant in time relative to Q at the current instant in time is going to be the time increment delta t times Q dot of t. Well, that doesn't seem very effective, because where is the information about x in here? Well, the information comes from inverse Jacobian iterations. Assuming that J is an invertible matrix, so if J inverse exists, in other words, if it makes sense to invert J, then we get Q dot is equal to J inverse times x dot. And that is what goes in here. So Jacobian iterations are, you basically start with the Q that you have at the current time. Then at the next instant in time, you update that by multiplying your time increment, delta t, times J inverse x dot at your current time. And then that gives you your Q at the next instant in time. And then you repeat this process, and then what will happen is that this arm, for example, will march along the trajectory. I'm not drawing it very well, but somehow the lengths changed along the way, but that's not part of the algorithm. And so it will follow the trajectory and reach the end point. And we can use that same algorithm, and that's what this paper does actually, to march along a path, not in the xy plane, but a path in the space of orientations or rotations. You can generate an artificial path from what the orientation of the satellite would be if you choose some random values of alpha, beta, gamma, and generate a path to the orientation that you want to be at, and then that tells us what the actual angles alpha, beta, gamma need to be in order to reorient the satellite in the way that we want. So we'll talk more about that next time, and I'll go into more detail on this, and we'll have a homework on Jacobian iterations, because that'll be a good lead-in to the discussion of robotics as well. Okay, any questions?
The makeup still planned for next Monday?
So I have not reserved the room yet, but we can certainly do that, yes. And I'll send an email out when I know about the room. Okay, well, have a good Thanksgiving. I didn't assign very much homework to you, so you, in principle, could even do it before you get home or wherever you're going. So I'll see you the Monday after, well, next Monday.